Right, these are your examples for section 16.3, looking at the KB expressions. So starting off, for each of the following weak bases, write the chemical equilibrium equation and the equilibrium law expression for KB. Okay, so we start off, this is our weak base. So Cn minus aqueous plus water, and all of these will be plus water. We got double-sided arrows. It'll form our conjugate base plus hydroxide. Okay, they'll all look similar to that. Again, like the general one, this would be our weak base, so B, and then this is HB, our conjugate acid for that. Our KB expression, KB, is equal to products, so HCN times the concentration of hydroxide divided by the concentration of our weak base. Okay, so that would be what it's asking for there. Okay, SO4 2 minus, so we have SO4 2 minus plus water. Should write down the states always. It's going to produce HSO4 minus plus OH minus. Okay, and the KB expression for this, we have our conjugate conjugate acid times hydroxide divided by our initial base. And that's as much as we need there. If we need to find our KB, we can use our data booklet, go KW divided by our KA to then find our KB. If it has our KB, sometimes we won't have that information. Okay, next question. So the hydroxide ion concentration is 0.157 moles per liter for a solution of sodium propionate. Okay, is found to be 1.1 times 10 to the 5 moles per liter. Calculate the base ionization constant for the propanoate ion. So our formula here, so we start C2H5COO minus. Again, the Na, as soon as we put in water, that Na splits off and becomes a spectator ion. Not needed. We just need this part. Okay, this is our base that is acting in this. We add it to water. Okay, and it's going to produce C2H5COO. H. So that H will go from there to there. Okay, plus OH minus. Okay, for this one, so write out our ice table. Okay, and if you ever aren't sure, draw an ice table. Okay, they can always be helpful, and sometimes it's helpful just to see that you don't need the ice table, and so on. So just split it up. We don't need water. It doesn't have a concentration. So it says we're given the hydroxide ion concentration. This concentration here is 0.157. And so we know that like, this is 0, this would be plus x, so this is going to equal x. Okay, this would be 0 plus x, so this is going to also be 0.157 because it's equal to x. Okay. Or sorry, I did this wrong. I read this question a bit wrong. So the hydroxide ion concentration in as 0.15. So this is 0.157. Okay, and that's why this one's worded really weird, but this is the concentration of sodium propanoate. Okay, and then this is the concentration found down here for our 1.1 times 10 to the minus 5. This is for our hydroxide. So then this would also be 1.1 times 10 to the minus 5. Okay, this will be minus x. So we just now calculate. Okay, and this number, when we go minus x, is so small that this stays 0.157. Okay, now for our Kb, it's going to be our conjugate acid, okay, times our concentration of our hydroxide divided by our concentration of our weak base that we started with. Okay, put our numbers in. So we got 1.1 times 10 to the minus 5. Both these numbers are the same, so I'm just going to square it and then divide by 0.157. Okay, and we get our Kb is equal to 7.7 times 10 to the minus 10. Oops. Okay, will be our Kb. Okay, if the pH of a 0.10 mole per liter aniline, okay, so which is C6H5NH2, solution was found to be 8.81. What is the Kb? So again, we have our weak base, C6H5NH2, okay, plus water. It's going to produce C6H5NH3 plus OH minus. Oh, this way the camera's having troubles focusing. Okay, so here's our reaction. Our base with the water produces our conjugate acid and hydroxide. Okay, we'll again do our ice table. Okay, and this doesn't matter here. Okay, so we are given 0.1 moles per liter solution to start with here. Okay, and then we found that the pH is 8.81. So that's going to help us solve for this. So again, these will start at 0. These will both be plus x. This one will be minus x. So this will be 0.10 minus x. And then both of these will just be x. Okay, again, pH is equal to 8.81. Okay, which means that the pOH will be 14 minus 8.81. So the pOH is equal to 5.19. And then the concentration of hydroxide is equal to 10 to the negative 5.19. So we get our concentration of hydroxide is equal to 6.45 or 46 times 10 to the minus 6. Okay, so that equals x. 6.46 times 10 to the minus 6. So now we know that both of these values are 6.46 times 10 to the minus 6. And then if we go 0.1 minus 6.46, really we got 0.1, so this doesn't matter, it's so small. So now we'll put it into our Kb formula. Concentration of C6H5 NH3 times OH. Okay, so that'll be our Kb equation. Okay, put our numbers in for our Kb. Again, because both these numbers are the same, we'll go 6.46 times 10 to the minus 6 squared and divided by 0.10. So our Kb is equal to And for significant digits, we have 2 here, and remember, only the numbers after decimal and a pH count. So we have 2, so we got 4.2 times 10 to the minus 10 would be our KB value. Okay, for this one here, so it's a combined question. Find the hydroxide amount calculation, the POH, the pH, and percent reaction or percent ionization for a 1.20 moles per liter solution of baking soda. Okay, so baking soda is sodium bicarbonate. So this is NaHCO3. Okay, so really, again, we put this in water. We got HCO3 minus, that's going to be our weak base. Okay, plus water. It's going to produce H2CO3 plus OH minus. Okay, so that's the reaction that's taking place. Okay, we'll put our ice table down. Okay, split it up. Cross that out. Okay, so we know that this is 1.20 moles per liter. Okay, we know it's going to be minus X, so we got 1.20 minus X. These are both starting at 0. They're going to be plus X. And so these will both equal X. Okay, so that's some of the information. We also know the Ka for this. So the Ka for that'll be carbonic acid. Okay, we can just look on our formula sheet. Okay, and the Ka for carbonic acid is 4.5 times 10 to the minus 7. Okay, and that's one thing to note with this one. You can find the Ka for this, but that's where this is acting as an acid. Okay, we want the Ka for its conjugate acid, so that's why we find the Ka for carbonic acid. Okay, so just be careful with that. Okay, and so we found this, so that means the Kb will equal the Kw divided by our Ka. Okay, put those numbers in. Or sorry, Kb is equal to 1.0 times 10 to the minus 14 divided by 4.5 times 10 to the minus 7. So our Kb for this equation, 2.2 times 10 to the minus 8. So that's the Kb for this equation here. Okay. Our Kb equation we have, like for this, we have our carbonic acid times the concentration of hydroxide divided by the concentration of our initial base. So, okay, we'll do a quick check, rule of 1,000. So rule of 1,000, we'll put 1.20 divided by 2.2 times 10 to the minus 8. And this is greater than 1,000. So we know now we can get rid of this minus X. So let's put the numbers we know in here. So we know 2.2 times 10 to the minus 8 is equal to, we have X times X, so X squared over 1.20. Okay, so now we can solve for X. So we'll times both sides by 1.20. That cancels with that. So we got X is equal to, and we want to square root both sides to get rid of the squared. So X is equal to square root of 1.20 times 2.2 times 10 to the minus 8. Okay, so X is equal to 1.62 times 10 to the minus 4 moles per liter. Okay, so that is now our values here and here. Again, so we want to find the hydroxide amount concentration. So this is our hydroxide amount concentration is equal to 1.62 times 10 to the minus 4 moles per liter. Okay, so this is our first answer here. Okay, now we want to find the POH. So POH, I'm going to go over here. It's equal to negative log of our hydroxide concentration. Okay, so negative log. We got our POH 3 point, and for significant digits too, so we have 3 here, so we have 3 here, which means for our POH, we're going to have 3 after the decimal, 3.789. And then to get our pH, so this is our second answer we have. Okay, our pH will equal 14 minus our POH, 3.789. So our pH equals 10, and again, the decimal, after the decimals, they're the only ones that count, so we got 211, 10.211. This is our next answer. Okay, so we have this, we have this, we have this. Okay, now we have to find our percent ionization. Okay, now we just have to solve for percent ionization, which is equal to our concentration of hydroxide divided by our initial concentration of our base times 100%. Let's put those numbers in. Our concentration, 1.62 times 10 to the minus 4 moles per liter divided by 1.20 moles per liter times 100%, and our percent ionization is equal to 0.0135%, so a really small percentage. Okay, so that's the other thing we had to solve for. Okay, so again, like with these problems, easiest, write down, kind of always start with your equation, write an ICE table, even if you don't know if you'll need it, okay, and then just start solving for what you can solve for. So in this case, we solve for our KB, then we used our KB to solve for our concentration over here. From there, we could find this, this, and then finally this. Okay, I'm going to do this last page on next video just to make the videos a little bit shorter.